coming from it. And we are here today to hear from two of the industry specialists who are ready to give us their knowledge and also their experiences in their work. Also with me, I am supported by my wonderful crew. I just wanted to take a minute to introduce them. So first, I am supported by my vice chair, Rashid. Hey, Rashid, if you want to come off mute and give
Yeah.
a little intro.
Hello. Good morning. Good morning, everyone. Thanks, Josna. Abdul Rashid. You can call me Rashid. I'm the vice chair of this chapter. Happy to have you here. Thank you so much for accepting our invite and agreeing to sharing your knowledge with the whole group here. Thanks again.
Thank you, Rashid. And I'm also supported by our membership chair, who is Kader, who is also hosting as ACM Richmond today. So over to you, Kader.
Yeah, hi, this is Khadr Wali Sheikh, and I go by Khadr. I'm the membership, I volunteered the membership chair for this chapter. And yes, welcome and thanks for your time to sharing your thoughts and sharing your knowledge to the group. And we look forward to work with you and coordinate in the future assignments. Thank you.
Yeah, so I next follows up. We do have two roles, secretary and treasurer, who work interchangeably. That's Karthik and Ankita. Karthik and Ankita, if you want to give yourself a bit of intro.
Hey everyone. Yeah, I mostly work as a treasurer for ACM chapter, and welcome all to the session. And thank you so much for joining. And we can collaboratively work together to make the technologies, recent technologies, talk about that. So thanks everyone.
Thank you.
Hey everyone, Karthik here. I'm excited to serve as the secretary for our ACM chapter. Again, I help the team here, with the collaboration activities and trying to build a very productive and engaging community here. Yeah, thanks.
Thank you. Also, we are completely supported online, offline with all the internet activities by our webmaster, who is Dipanjan. Dipanjan, thank you for everything. If you want to go ahead and introduce yourself.
Yeah, sure. First of all, glad to be part of this community and just wanted to welcome the speakers for your time and sharing this knowledge with all of us. Thank you very much.
So without further delay, while I will try to introduce the first session from, so you are there, right, Vidisha?
Yes, hello.
Hey, hi, Vidisha. So Vidisha will be taking us over to her topic for the next 20 minutes, which is followed by questions. And then we would have Ajay pick up the topic, pick up his topic on agentic AI and then drive it to the questions. And then we will have some conclusion notes. That's how the agenda ends. Thank you, Vidisha, for accepting
Thank you,
it.
everybody.
Yeah.
Good morning.
Over to you, Vidisha.
Okay, so I can share my screen. Is there? Let me know if you can share my, you can see my screen.
Yes, we can see your screen, Vidisha.
Okay, perfect. Firstly, again, thank you so much for the opportunity. And I'll give a brief introduction about myself. I am Vidisha. I work as an independent AI researcher as well as a senior data scientist at CVS Health. And today I'll be talking about building reliable AI agents. That is how we build them, how we build the AI agents, and what is the gap between building AI agents and evaluating them. And we'll go through different methodologies on how we can evaluate those. So yes, so let's start with where we are right now. So in 2022, LLMs were just used to answer questions. In 2023, LLMs were used as tools and browse the web. And in 2024, LLMs could orchestrate multi-step workflows autonomously. And today, it's 2025, 2026. Enterprises are using agents to uh, build real world consequences, like customer agents, financial analysis, document analysis, and it happened overnight. So right now, over 80% of the Fortune 500 companies have active AI agents deployments. Frameworks that were just side projects like LangChain, Llama Index went from side projects to production infrastructure within 18 months. But here's what didn't keep up at the pace: the evaluation methodologies. So, the research communities always spend decades building robust frameworks for classifying models, NLP models, and singleton LLMs. But with agent and it this transition took years, but with agents we didn't get this time. It happened overnight. So right now we are deploying way faster than we are evaluating, and this talk is about closing that gap. Yes. So I'll go through a case study, something that I worked recently on. So let's say we built a document processing agent to extract key clauses from contracts. It was tested on clean 50 documents. All the evaluation suite passed, and the team shipped it with confidence. So, but what happened 3 weeks later was a human reviewer noticed that the agent had been silently dropping clauses on every contract, and that where the clause appeared after page number 8. The context window was quietly truncating. The output looked very clean. The confidence scores were high. Formatting was perfect, and nobody knew. So the point here is the agent didn't crash, it didn't throw any error. It just wrote a very polite, well formatted summary with critical clause missing every single time. So that's the failure mode no one talks about, and that's what the agents are not trained for as well. So that's the point here, that I'm not here to tell that the agents are bad. That I'm here just to discuss about what happens when we ship the agents when the right evaluations are not in place. So we can do a quick poll. So have you ever built or worked with AI agent in the last year? Although I can't, let me just see if I can see the screen. Right. And have you ever deployed one in production? Right. And the last question, which is why we are here today: has one ever done something unexpected after deployment? So yes, I think that's the last one is the interesting one. And I think that's because it hasn't happened yet, or because even when it happened, it was even hard to tell. That's exactly what we are here to talk about. So let's talk about how agents fail, and what are the 4 big failure modes. So agents don't fail like the traditional software fails. And these are the 4 failure modes that I have seen repeatedly, and I'll discuss them in detail. So first one is the hallucination mid-chain. Hallucination in a singleton LLM is annoying, but hallucination in a multi-step agent is catastrophic. So for example, let's say model fabricates a fact in step 2. Every downstream step builds on that lie. That fabrication becomes the ground truth. So by the time final output, the error is 4 steps deep. but the funny thing is it looks completely confident. The second one is the context drift. So the agent loses fidelity to the original goal across long workflows. Complex, nuanced tasks just become simplified. That is, our goal becomes very narrow, very small, and the scope has reduced over time. The third thing is the tools misuse. So agentic systems can choose their tools dynamically, and that's the point of it. But we never know what kind of tools are the agents using. Are they using the right tool with the wrong parameters? Are they using the right tool in the wrong sequence or the wrong step? Or if it's using the wrong tool completely? That the thing is that with if it was a human, it'll stop, it'll take a pause, and it'll review it. But with AI agents, there is no hesitation, it just proceeds. So this is about the tool misuse. And the fourth one, I feel like it's the most dangerous one. That is, the agent can return a well formatted, confident, completely wrong answers. There's no error message, no low confidence flag, just a clean response a user might act on. So now let's talk about why are we not able to catch these failures. So what generally teams use are some of the metrics are like accuracy. That is, did the final answers match? Blue or the rogue scores? Does the output resemble a reference? Or the user satisfaction ratings, that is thumbs up or thumbs down. One thing that's common in these metrics are it's trying to evaluate the output in isolation. What these metrics are actually missing is whether the reasoning chain was sound, whether the tools that were used were correctly along the way, and whether the output holds on a different phrasing. So, what happened is the eval suite passes, you ship, and but when in the actual scenario, when the user asks the same question with slightly different paraphrasing, the agent takes a completely different reasoning path, maybe uses a different tool, and returns a different answer. Which one was right? It's really hard to know because we evaluated the destination and not the whole journey. So, yes. So what does a good evaluation system look like for agentic systems? So this is a framework that I generally use, and it's built across 4 dimensions, and I can talk about each of the dimensions. So the dimension 1 is the faithfulness. That is every claim grounded to the source material? Is there any hallucination? So, for example, a faithfulness score of 1 means every statement is traceable back to the source. And below 0.8 in production should maybe trigger a manual review. Dimension 2 would be the task completion. So, it means like, did the agent accomplish the full end to end goal task or just like 70% or 80% of it? And this requires explicitly doing what done means here. So that is something that the teams need to specify very explicitly so that it forces basically clarity on success criteria. And this is something that the teams generally do. And for this step, you would need some inputs from this SMEs, product team, and leaders as well. Then come the tool use accuracy. That is, are the right tools, right parameters, and right sequences are used. So this is very specific to agentic systems, and there is no equivalent to singleton LLMs for this. So it's very important to log every tool, every call, and compare it with against the ground truth or the expected sequences. The fourth framework is the trajectory consistency, meaning if the reasoning path was coherent across all the steps. So basically, did the agent maintain fidelity to the original goal? I feel like this is the hardest to implement, but it is the one that catches failure, which the three dimension miss. So coming to, I think knowing how to evaluate is only half of the equation. It's also more important to understand how to structure the evaluation. And I think it about as a three-layer step. And most of the teams I feel like worked on the first layer and second layers, and third layer is where for agentic system we catch most of the failures. So the layer one is the unit evaluation. That is, test each tool, each retrieval step, and each prompt in isolation. This is very fast, very cheap, very easy to automate. Basically, it tells us how each piece and how component works. It doesn't tell you anything about how these pieces interact or the how the pipeline works. Layer 2 is the integration evals. That is, test the full pipeline end to end on 50 to 100 curated data set of data set developed by SME's product and use that as a ground truth. This basically catches interaction failures and checks if the pipeline is working, which the unit evals missed. This is basically checking the whole pipeline health of the system. And the layer 3 is adversarial evals, which is deliberately try to break your agent, feed it with ambiguous, conflicting edges, ambiguous inputs, conflicting context, edge cases, out of context queries. This is where most of the production failures actually live, not the happy path, basically. So if you are able to set up this, it will eventually catch most of the failures. Now let's move to, let me show you how this works out in actually practice. So let's say we build a multi-step document analysis pipeline. The agent reads multiple long documents, identifies contradiction across them, and produces a structured summary for human review. It's a multi-step pipeline. It retrieves, compares, flags, and summarizes the document. So now what went wrong here? So during the evaluation, we see that the layer 1 evaluation is clean, layer 2 evaluation passed, the team had confidence. But when we ran the adversarial evals, something surfaced. The agent wasn't just flagging the contradictions, it was resolving them on its own, and it was silently picking one source over another. Instead of flagging them, it was completing the task while resolving the most important signal. So basically, it tried to decision itself. And that's where the biggest flag out here is. So layer 1 and layer 2, although the layer 1 and layer 2 evals passed, but the layer 3 failed, and that's how we catch the failures. The fix is straightforward once we know it, just to add a explicit contradiction flagging step and a faithfulness check at the aggregation layer. That's how we would be able to catch it. So again, what does a production ready agent actually mean? It's again not a well-defined definition or a milestone. I feel like any agent is a perfect agent doesn't mean that it never fails. It it it'll de- it's a AI system. It'll definitely fail, but a good agent is the one that fails gracefully. Meaning, like when it doesn't know something, when it fails, it says so. It doesn't just resolve the conflicts on its own. And that's something has to be built as a feature. it doesn't come on its own. So that is first bar, I feel like. The second I feel is the behavior is consistent for that agent. That is, if we have a semantically equivalent input, it should produce semantically equivalent output. It shouldn't be just a lucky guess that you get lucky and you get a right output. The third is that every decision should be traceable. So, meaning by looking at the output, you can actually tell which tools were called, which path was chosen, which parameters were used, and most importantly, why. And this decision should be traceable by anyone who is looking for the output. The fourth one is all the edge cases are tested, meaning the evaluation suite should include inputs that the agent wasn't designed for. Basically, all the edge cases out of sample distribution that the user can actually input in future. And the fifth one, the most important one, is that the fallback should exist. Meaning, if the confidence is low for any output or something happens, there is a flag for human review, or there's a withheld response, or some kind of flag. So, I think most importantly, there are 5 questions that we need to ask before we ship an AI agent. The first one is, what does the failure look like? And will you know when this happens? The second one is, have you tested the inputs your agent wasn't designed for? Third, can you trace the reasoning, not just the output? Fourth, what happens when the confidence is low? And fifth one is, who is accountable when the agent is wrong? And defining the accountability before you ship is something really important, not just after something goes wrong, but before, more proactively than in a reactive way. So yes, again, key takeaways from this talk would be like, agents fail differently than traditional software, and evaluation is something that must reflect that. Uh, Output quality metrics are really necessary right now. It's not just sufficient. So we need to have different checks, including faithfulness, task completion, tool use, and trajectory. The third would be build all 3 layers, that is unit, integration, and adversarial. Most teams stop at layer 1. And production readiness is a bar that is again defined from team to team, and it has to be done explicitly. It's not a checkbox that you need to pass. And lastly, teams shipping reliable agents invested in evaluation before launch, not after. So that should be all from my end. Again, thank you so much for this opportunity. And feel free to connect with me on LinkedIn. And looking forward to speaking with you again. But before that, if there are any questions.
Yeah, thank you, Vidisha. So, this is Khader. So, I just want to to tell you, this is the most required topic in these days. Actually, this is I'm saying from my personal experience. So, from more than 2 years, I personally using the either it is a Gen AI or agentic AI, where we made that part of the life. But every day we notice the result of the Gen AI or agentic AI is not accurate.
Exactly.
So every day, it's like, we cannot simply take the result and we cannot use it blindly. We cannot at all, because sometimes it's completely giving the, I don't say wrong answers, but it's not accurate answers. So it's not like take it and use it. No, whenever you
Yes.
give, the result is not like so. We have to definitely, either it is a generative AI or agentic AI, we have to validate the result, and we need to. So that means as a summary, I'm saying the user is not confident to use that agentic AI 100% blindly. So we have to do the validation from the user's perspective, and we need to approve the result yes, it is accurate, that then only we can release. Yes, yes. I mean, so I appreciate for bringing this topic, because this is most needed one in these days.
Yeah. And I feel like specifically for the non-technical audiences who are very skeptical about using these technical
Yeah,
products, they are like really unsure about what if something, yeah, something wrong happens or something
exactly,
really out of the place happens.
exactly,
Yes.
exactly. Yeah. Thank
Yeah.
you.
Thank you so
Great work,
much.
Vidisha. Like it really provides the blueprint, which is really needed in this world, especially as you touched things, right? There are AI architects, there are people who are using AI. So
Yeah.
there is clear distinction, and then these are the concepts which elevate them from just using AI for questions to someone who is actually using AI for the right purposes. So rightly nailed. Maybe we can dive into the questions if someone have any.
I know we are at time as well, so it's okay. We can connect over LinkedIn as well. I just don't want. Yeah, I know Ajay has to present as well, so no worries.
Sure, yeah. Yeah, we can have the questions at the end. Like,
Yeah.
I mean, there will be like still 10 more minutes after
Mhm. Yeah.
Ajay's. So please go ahead, Ajay.
Yeah, okay. Let me share my screen. Can you guys see my screen?
Yes, Ajay, we can see.
Yeah. So shall we start?
Yes, please. Yeah, go ahead.
Yeah, hi.
Yeah, thank you.
Uh, yeah. Uh, Good morning, everyone. Thank you for joining today's ACM Richmond sessions. My name is Ajay Pandey. I am Director of Technology at Tradeweb Markets. I have spent like 20 years in leading and developing software system in the areas including distributed system, real-time systems, high volume messaging system. Currently, I'm in the financial technology, and in my past, I worked a lot in telecom softwares. So I have core experience in developing like C++ real-time applications. Before we start, I would like to thank ACM Richmond and the chapter leadership, for providing the leader this opportunity to speak here. And thanks for the audience for joining. Okay. So today we are going to talk about building resilient real-time system, uh, and I will talk about the architectural strategies for managing when there is a event surge. When I talk about the event surge, it is like the sudden spike in the request all of a sudden for the software. So when we talk about the real-time system, what does it mean? It is like a system which is like high volume event system, real-time system, which takes the input real-time data, process it, and gives us some output within the specified time, like I have shown in the picture. Like it has a lot of characteristics, like it has to be redundant, it has a redundancy, fault tolerance, monitoring, it should be automatically recoverable, and it should be scalable. So these are the real-time characteristics of the real-time system. And more than that, it should process the input. It will take the request and process the request within the specified time duration and process and give us the output. So it is predictable, the output is consistent, and all those things. There are so many things, but most of it is like the output should be consistent, and it should be predictable. It is not like some every time it is giving different output for the same input. So this is the basic definition, or we know what a real-time digital system is. But when we have seen that many real-time system like GPS, financial systems, telecom, like call processing system, like when we make a call, the call is not connecting. When we are doing a trade, the trade is not going through. When i'm when i'm plugged into a GPS system, that GPS is not giving me the correct location. So these are the typical example of the real-time system, but sometimes they are, like in the high peak or some kind of adverse situation. These things doesn't work. When these things doesn't work, like these, when I'm saying these things, meaning I am talking about the real-time systems or the real-time softwares. We often think that uh, we often think what has happened to it. Is it a bug in the code? Is it we always think that, hey, there is something bug in the code, but it is not always the bug in the code. It is like the design that we have used to develop the software is not correct. It is not always a bad code that has got to the outage of the system. Like in when we talk about the event surge in this slide, like what is event surge? It is like a sudden spike of events that has come to the system, and system is not capable enough to process it. Like in case of stock market, because of some economic change, all of a sudden there is a spike in the event for all the things. There are too many sells and buy in the market, and your system is designed to handle like thousands of requests per second, but all of a sudden it receives like 10,000 of requests per second. Or in case of, let's say, in case of Thanksgiving Day, you got a good deal. Every stores are giving a good deal, and all of a sudden, there are sudden spike of events in the retail shop or any software, like Home Depot, Lowe's, or whatever it is. Like they get a lot of spike all of a sudden for 6 hours. So are they capable enough to handle those event spike? So those are the things that we have to take care when we are designing the real-time software system. So this is like event search. I speak about here what is event search. So what happens, when the system doesn't keep up the capacity when we receive the spike of the event? Like what happens? So generally what we feel, based on my experience, like when system is designed to handle thousands of requests per second, and all of a sudden it starts receiving like 10,000 of requests, we see that, delay in the processing. Like uh, the the process that the request that enters the system, we see that the request is not processed within the same time. It takes a lot of time. Like we have seen many times in the in the system, like your system, we say that, system is lagging, or system is hanging, or or it is not showing the correct answer, or it is, these are the things. So we have seen that it increases the latency of the processing. And what are the other things that happens is the outage. The website is not available because of the surge of the request all of a sudden, which they are not ready to handle. It is not reachable at all. That website is not available, or maybe that software is not available. And what are the other things that can happen? The financial impact, like there could be a revenue loss. They might lose some of the market opportunity to buy or sell, and maybe selling the product, or selling anything, or buying something, or maybe they lose the subscribers. So these are the this could lead to the financial impact of the company. There could be some reputational impact, right? They might lose the customer. There could be some regulatory fine because of that. They could not process those things, such critical things at that time, and they could not keep up the market, and regulatory can fine them. So these are the things that can happen when software doesn't keep up the things in case of there is a high traffic or event surge. So I just talk about that thing just now, that what are the failure patterns, like I told, like, the latency. So what happens, why the latency happens? Because there are so many things already gone into the queue, and your system is not able to clear the queue within the specified duration of time, and it can explode, it can crash. I mean, the system, the queue is just blown up. It is ready to handle 1,000, but it is receiving 10,000 per second. So it goes, the queue, the queue size keeps growing, and after certain limit, it crash. It can lead to another problem, the system slowness. What could be the reason for system slowness? Like, when the system is slow, the client retries. That retries creates another traffic to the system. So we are already on at the attack of so many surge. At the same time, the client is also retrying, so it is adding more requests to the system. So it is like, it is creating even more load to the system, and system gets slower and slower with the time, and at the end it will crash. The other pattern could be like, one system is dependent on another system. Like, one service A is dependent on service B is dependent on service C. Now let's say service B is connected to both service A and service C. They are cascaded, they are like connected, linearly connected. And if service B crashes or got attacked by the it was like got a surge because of some request from service A. So it is like, and it got delayed, so it has an impact on the downstream component like service C, and it has it can block the entire system, or maybe it will slow down the user experience. So this is called a like cascading effect, like cascading failure. Like, one service is connected to another service, and one service is down, then the whole service, whole system will suffer. The other thing could be like denial of service. Like, if the queue, like if you see the queue explosion, like if the queue is full and your system is at the capacity of using the request or using the resources, some of like database, like if you talk about the database, or if you talk about the CPU time, or if you talk about the memory, and everything is used up, it is full now, your system cannot process anything. So when the new request comes, it will not be honored, it will be like rejected. So the customer will say, hey, I'm trying to access the system, but it is not giving me anything, it is like denying all the service. So we will face the denial of service. So these are the patterns that we face when we have not considered the resiliency in our real-time system design. Like, it is not always the bad code that causes the system to fail. It is the design thinking, the resiliency, the non-functional, not always the functional things cause the system to fail. Is it the non-functional things, like your resilient design that has been taken into the architecture, most importantly at the time of event surge, will cause, if it is not taken properly, it will cause your system to fail. So what is resiliency design? What are the principles? So there are many things think about, uh, your real system. uh, think in your real system to make it resilient. Like, if the system is receiving lot of events or lot of tasks to process, so you can think of like, let's say your system is designed to process 1,000 requests, and you are getting 1,000 requests at one shot. So your system should decide, hey, what is important and what is not necessary. Like, it might be the case, like, you are getting repeated updates or request for a same key or same task. When I'm talking about the task, let's talk about same key. So many system, process the data that is no longer needed. Like, it is out of 10,000, they are getting repeated request for the same thing, and they are processing it, they are keeping in the queue. CPU time is getting exhausted, memory is getting exhausted. But the thing is, like, does your system identify, hey, this is not something that new we have got, it is the same thing that I'm getting every time, again and again, so I should just ignore it, throw it out? Or, there could be some many strategies through which we can reduce the unnecessary work in the system. And that makes sense, like, it will give less, it will reduce the pressure of the system, first thing. And second thing is that it will reduce the amount of output. It will not generating, like, it is getting 1,000 requests, it will not generate 1,000 output for 1,000 requests. It might reduce it to, like, say 1,000, if you are getting repeated request. Okay. The second principle is the control demand. Like, your system, every system has the capacity. Okay. So when your system exceeds the capacity, when our system exceeds the capacity, that's when the system will get impacted by the any adverse environment, and maybe it becomes unstable, the control demand. So we should, at the time of event surge, or when at the event spike because of some adverse situation, when your system is getting like lot of requests all of a sudden, the other principle that we can use, that, hey, we can control we can tell the producer, like whoever is generating the request, hey, don't give me so much of load. I am only capable to handle like 1,000 requests per second, and you are giving me 10,000 requests per second. We have to tell the upstream process or upstream system, or maybe the producer of the request. So this is another principle. The third principle is like prioritizing the criticality of each request. Like, your system should identify what is critical and what is not critical. Okay. So if there are a lot of requests and your system is getting compromised with loads of traffic, your system should know like which is important and which is not important. And the fourth thing is principle that we generally use is like, observability, like measuring and checking everything. Like, uh, you cannot fix something that you can't see, but something, there should be an indication before system gets into a bad shape. It gives some indication. So if you keep observing your system, it should give you the hint, like something is not doing good. Maybe the system is flickering, it is showing some abnormal things, the CPU time is high, the memory usage is high. So you should notice, and you should put an alarm in the system, like, hey, if the CPU time goes beyond 50% or 60%, send an alarm, to the support, like something is not good. So with that, we can protect our system, from any adverse situation. So this is about the principle. So now I'm going to talk about like whatever the principle I discussed here, like reducing the, so each principle has one name, like the reducing the unnecessary work is like event coalescing. So event coalescing is nothing. Coalescing means the merging, so you are getting thousands of requests per second. Your system is ready, but you are all of a sudden you are getting like storm of requests, you don't know, and your system is not ready to do that. So in that case, what we do, like as I said, your system should be capable of handling merging, or maybe throwing out the redundant request, and thus reducing the number of events being processed in the system. So let's say we are getting all of a sudden like hundreds of thousands of requests. Your system says, hey, I'm getting for this particular thing so many requests, I should not do that. I can merge based on the key. There are many strategies of achieving it, which we can talk later. So basically the thumb rule is like, I'm out of 10,000 things, your system will identify, segregate all the requests based on some key or based on some criteria, and try to reduce it, squeeze it, and try to, or maybe it will throw out all the previous one, and use the latest one. That is one strategy we use, and use the latest one, and probably that will make sense. We just, the stale requests are thrown out from the system. So this is called event coalescing, where we generally, your system is capable enough of merging all the things together, and make the the number of requests smaller, and those smaller requests will go to the downstream, so that even downstream component will not feel the pressure. of the storms of the request. So state aware event coalescing is like something that process the latest state, meaning if you think about of a if you think about the what do you say GPS system. Let's talk about the GPS system. When you are moving a car from location A, B, and C and D, sometimes if you see in your car, all of it, your car is stuck at one place. It is not moving, and all of a sudden it goes to you have moved took so many left and right, but all of a sudden it start giving the correct location. It didn't go like whatever you have already crossed, like you after, when you saw the last stuck position, after that you have take, like, let's say, two left and three right. It will not show all these things. Basically it reduced all those things. It threw all those stale requests, and it updated the latest location. So you think of that way, like always take the latest value, just throw all the old thing, when you are getting a lot of things or when your system is slow. So another thing is like stock price. Let the price of the stock is moving, okay, 100, 200, 300, or whatever, 101, 102. And sometimes, because of some event surge or some economic change, all of a sudden the volatility in the market is increases, and you are getting like a lot of price changes all of a sudden your system is getting. So what we will do, will you show like each and every price, that history of the price that your stock has gone through? No, you will just show the latest price. That is what the user is more interested in. User don't care like a stock has moved to 101, 102, 103, and then finally now it is 105 or back to 99. They are interested in like what is the final price, tell me that, and without any delay of the system. So this is one of the thing that we have faced and we handled. Another, in my telecom work a long time before, we have handled this thing in the presence server. Like presence server is like a system which will tell your presence, like whether it was online or offline or busy. So uh, if you are online, before that, if you were already offline, it doesn't matter. It should give the result like, hey, now the state of the user is online. So, and it will merge all the requests for many subscribers and give it to the downstream system. So, what are the benefits of this strategy? It's very simple. It is like it reduces the load on the CPU, it reduces the memory usage, the latency of the process request, like the time it takes to process one request will be lower. The output, like the throughput, meaning how many process it is processing, how many requests it is processing, those will become higher, because now your system is more smart to handle and throw out the redundant things and handle all the important things. So this is one of the things that we have to take care while designing the resilient event driven system. Like I said, this is one of the example just now I talked about. Like at the time of event search, your price movement is 100, 101, 2, and 3, and 4 all of a sudden, but your system is handled to, all these things happen within 1 second, but your system is capable to handle like one request at a time in 1 second. But all of a sudden, in 1 second, you are getting like 5 prices. What will happen if your system keep everything in the queue and try to process one at a time? What you will see in your dashboard, you will see the price is 100, then the price is 101, 102, 103, like that. Slowly, it is like a kind of lagging movement of the price. But user is not interested. User is interested, hey, tell me the current price. What is the price of this stock right now, which I want to buy? They should not be. And imagine, if they book the trade or buy at 102, but actually the price is 104, they can sue the system that, hey, I bought it at 102, but at the end of the time, your backend has priced me at 104. It's a problem. So these are the things, we should take care by resilient design. So this is one of the pattern that we follow to make our system more robust and more protect our system from like the high spike in traffic all of a sudden. So this is I took it from one of my present article that I wrote. So it is just an for someone who is more interested. Like I know the audience is both students, engineers, and engineering managers. So if somebody is any student or engineer who is more interested in designing the coalescing architecture, so this is like basically the layers are four important layers: ingestion buffer layer, coalescing engine. This is the main merging engine, and there is a dispatch layer. So in between, whatever the three component that you see is the main component of the coalescing architecture. The event producer is basically I have used it just for the sake of understanding. It is basically a multiple clients which are generating the request, and you have that buffer. This is basically the coalescing buffer where instead of using the traditional first in first out queue, we will be using the coalescing buffer. It's a kind of a special buffer which will put everything in the queue based on the key, and based on the key and based on some policy like merging policy, it will merge all the requests. So let's say this guy are sending like thousands of requests and pushing into the buffer, but this buffer is smart enough to merge all the requests based on some policy into, like with some time duration. It will take all the request for 100 and 300 millisecond of time window and merge all the requests, thousands of requests, into like some smaller volume of request. And there is a dispatch layer which will again do the batching of those requests and give it to the consumer. So basically the consumers, the dashboards or UI or whatever it is, so they will be more relaxed, they have a breathing space. But imagine a scenario where this guy are sending thousands of requests, and this is like blindly sending the thousands of requests to your dashboard will crash, because human reflex is not capable of seeing the like thousands of things at 1 second. They can only see the difference of like 300 milliseconds per second per request. That's what they can observe. They cannot observe like so many things at one shot. So it is very reasonable, and it will also reduce the load on the system on the downstream. So this is about the coalescing architecture. This is some of the matrices that I have faced, I have used when we use the traditional uh, first in first out queue, and when we are using for the resilient architecture, the coalescing queue. Like your events are getting thousands, and this is the 1,000 requests both are getting. But in case of FIFO queue, like first in first out queue, the hundreds of thousands requests are getting translated into hundreds of thousands dispatched requests. But in this case, it is reduced based on the merging policy. So see, the downstream sys component will only be getting like 4 to 8,000 or even lesser. And so these are the things. And now other thing, like it has many advantages. It is increases the CPU utilization. The memory users will be very reduced. Your consumer freshness will be like near to real time. It is not stale. Like your UI will not lag showing the bad things or the old things. Your UI will always show the new prices later, near real time. So apart from the coalescing event processing, the second principle that we have used is like back pressure. Whatever we discussed in that slide, like your system every system has a capacity, and it should process. It should tell the other system, the producer, that hey, you are sending at too high rate. You cannot send me at 10,000s of requests. You should only give me a request at thousands of requests per second. Like a restaurant analogy I will give for understanding. Let's say restaurant has like 100 seats, and all of a sudden 300 people came or 200 people came So it doesn't have a seat for 200 people, right? So what it does, it will tell the customer, hey, we have only 100 seats, and other people have to wait. Like other 100 people will have to wait, so that the 100, they will serve the 100 customer, and then later they will allow other. If 200 people enter, all of a sudden enter into the restaurant, it will be a chaos, right? So similar to that, it is like you have to tell the back end or the producer that you have to wait, you cannot give me such a load. We can achieve in the software using throttling or rate limiter. Like we can limit the rate of the software, and if we are getting high rate, we can reject it or tell the backend system or the producer that, hey, don't give me like that. You have to reduce. I will reject it. The third is like load shedding. Like as I said, you have to determine which is high priority and which is low priority. So all the high priority will be processed first, and the low priority will be dropped. It is like a lifeboat, like 100 people are drowning, and the boat has only 50 seats. It cannot save 100 people. It has to first secure the boat and save at least 50 people. Otherwise nobody will be saved. So a typical diagram, like incoming request and critical traffic will be processed, and the non-critical will be dropped. And the fourth principle and fourth and final principle, what I used is the observability. Like you have to measure everything, and system will measure everything. None of the system fails automatically. It will give some indication before it fails. So you have to observe the system, like CPU is growing up, memory is growing up, and all those things. So this is easy. I mean, everybody does that. But the first two the principles that I've used, the observability and the back pressure, those are the important things that we have to take care. So these are the key takeaways, for the peak, resilient architecture, and off peak. And when there is a peak, how to take care of that. The important thing is like coalescing design, back pressure, and the load shedding and observability. Among that, the first two is very important. Second two, the last two, we generally do take care all of by default, but the first two is very important. Thank you. So that's all from my side. And if you have any questions, feel free to ask me. Thank you.
Thank you, Ajay. Thanks for taking the time to show us or share your knowledge. I know it's out of time, but let's give 1 or 2 minutes to see if anyone has any questions, and before we wrap up.
Yeah. Thank you, Ajay and Vidisha. This is great. And I hope that you continue your journey and come often to ACM Richmond to present more of your advances, because overnight the advances are taking. So we are here to listen more of your work in future too.
Yeah, we are also partnering with IEEE, so we'll have more updates soon. And if so, I think we will have more opportunities to collaborate, like hackathons and lightning talks, those kind of things. I cannot say a confirmed date yet, but we'll have something for sure very soon, and that would open us more opportunities to collaborate. And we are also still looking for more speakers and collaborators. So just in case if you want to pass the word to other people, please do so. And yeah, thank you so much, Ajay and Vidisha, and we'll be happy to collaborate more in the future.
Yeah.
Yeah,
Also,
thank
one
you.
last thing. I know that many of you have already submitted some interest, but our team is really finding it hard to get some time to give you the best of the topics. So please bear with us. We will get back to you. All your requests would be answered, and we'll give you a chance, case by case basis. So don't lose their interest. Please attend, even if if you're not being a speaker.
Yeah. Thank you, ACM Richmond and all the chapter leadership, Rashid, Josna.
Yeah, thank you, Ajay.
Yeah.
Thank
Thank
you.
you, everybody.
Thank you.
Yeah, thank you.
Thank you, guys. Yep.
Bye.
Yeah, have a good one. Bye.
Yeah. Have a great weekend, guys.
Thank you. Bye.
Bye.